Let me begin. So this one you've probably heard before. John 14:6. Jesus said to him, I am the way and the truth and the life. No one comes to the Father but through me. So kind of unambiguous, I think. But anyway, I'll begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for this class and for these students. Just help us to understand more about your creation today, especially about the determinants, Lord. In my prayer, Lord Jesus. Amen. All right, so I defined for you guys last time the determinant, right? And I gave you this beastly general definition for it in terms of the, antisymmetric symbol. So this is over n sums. And we looked at a number of properties of the determinant, right? It's what's called multilinear. So if I can split up a linear combination in a particular column, right? And then the determinant of that sum is the sum of that determinants. We can pull a constant out, right? So like determinant of c times a, we found out was c to the n times determinant of a, right? That was the thing. We also learned, and I certainly haven't proved this, but it is true, and there's a proof in the notes that's rather technical, which is the determinant of the transpose is the determinant of the matrix. If you look at the proof of that in the usual mathematical notation, it involves sort of this sneaky rewriting of a summation over all permutations in a different way. But we agreed we don't know what permutations are yet, so yeah, you're welcome. So there's that. What else do we know? One of the things I said, but maybe I didn't, I should write on the board, is like if you have a1 0 an, if there's any column which is 0, the determinant is 0, right? And because the determinant of the matrix is equal to the determinant of the transpose, it also means that if there's any row which is 0, the determinant's 0, right? If you column swap or row swap a matrix, the determinant before and after is off by a minus, all right? These things are easier to say in words than for me to write down the formula, for sure. Let's see here, what else can I tell you? Towards the end of class, I told you that the determinant of a diagonal matrix, right? If you got diagonal matrix, d1, d2, dn, and they're the diagonals, the determinant of a diagonal matrix is the product of the diagonals. Well, that's nice. I mean, if you got a diagonal matrix, the determinant's super easy to calculate. But there's a bigger, badder version of this, which is that the determinant of a block diagonal matrix. If I have blocks, A1, A2, AK, suppose that I've got a block diagonal matrix. And here, of course, the blocks are square blocks. Okay, that's always assumed. When we talk about a block diagonal matrix, you're talking about square blocks down the diagonal. And as such, we can define the determinant of each block. Remember, the determinant at its base is only defined for a square matrix. But this is actually the product of the determinant of the blocks. Again, I'm not going to prove this, but it is true. And if you were a glutton for punishment, you could try to come up with an explicit, concrete proof of that. But it wouldn't be easy. But that is true. The determinant of a block diagonal matrix is the product of the determinant of the blocks, which is... So if you got a block diagonal matrix, calculating a determinant isn't so bad, is it? But there's more. Another theorem, which is pretty easy to prove, is that if you have a lower triangular matrix, so say like L1, L2 to Ln, and you've got non-zero stuff down here, possibly you got zeros up here. So lower triangular matrix, it is the product of the diagonals. Just, again, the product of the diagonals. Guess what? If you have an upper triangular matrix, so non-zero stuff up here, zeros down here, guess what? The determinant is the product of the diagonals. All right? So if your matrix is diagonal or block diagonal, lower triangular or upper triangular, the determinant is super easy to calculate, right? And all of a sudden that LU decomposition, which seemed like, it's kind of, it was kind of, now all of a sudden it's super nice, right? Because if I do have the LU decomposition of a matrix, like say that A is equal to, I don't know, 1, 2, 3, 0, 0, minus 2, 17, 1/13 times, I don't know, 7, 1, 1, 0, 0, 0, minus 9. What's your favorite number? What? 4. Okay. Anybody else? 22. I got room for one more. Okay, great. Then the answer to this is 1 times 2 times 3 times 7 times 1 times 1. It's, 42. What do you know? Obviously an accident. But, See, because the determinant of a lower times an upper, what did I just use? I used the next thing, the next tool in our arsenal. This is, so I haven't shared with you yet this, but this one's a big one. The determinant of the product of two matrices, A and B, is the product of the determinants. And in the list of all the things I'm not going to prove for you today, this is by far the most important one. The proof of it is in my notes, all right? And the proof goes something like this. I'll just tell you the proof in words. First of all, you can prove that the determinant of an elementary matrix times another elementary matrix is the product of the determinants of the elementary matrices multiplied. So this is true for elementary matrices. Then you can prove this identity is true for invertible matrices. See, because any invertible matrix is the product of elementary matrices. And as such, if you have two invertible matrices, when you multiply them, you've just got a product of elementary matrices all the way down. So you can just apply the determinant identity, product determinant identity for those elementary matrices all the way down and reconstitute into that identity. If one of the matrices, on the other hand, is not invertible, then you can prove that the determinant is 0 in both ways, all right? And it would take me a solid hour of class to prove that carefully, and it is deeply rooted in the construction of elementary matrices. This is a technical lemma, which is, I cannot emphasize to you enough that when you use this, you're doing something that's really a little bit nefarious. Like it's a nasty formula. There's a lot in here, all right? Any questions so far? Okay, so now that we have all this on the board, let's think about the theory that we've thought about before a little bit more. So let's think about this. What was the deal? What was the deal for an invertible matrix? What defines that? But essentially, we've got what? A times B equals to the identity, right? We usually call B the what? The inverse matrix, right? So what happens when you, or if you like, you could say, let me just say A times A inverse for the sake of specificity here. Take the determinant of this. What do we get? The determinant of AA inverse is equal to the determinant of A times the determinant of A inverse, which is the determinant of the identity matrix. But well, the identity matrix is a diagonal matrix where all of the diagonal entries are 1. So what's the product of 1 times 1 times 1 times 1 times 1? 1, right? I can do that one even at 815. So there you go. And so this shows me a number of things. One of the things it shows me that the determinant of the inverse matrix is 1 over the determinant of the matrix, which is ever so cool. That's a theorem. If the matrix is invertible, then the determinant of the inverse matrix is simply the reciprocal of the determinant of the matrix. This is an easy one to remember. But there's something deeper here. See, we can go back to our theorem, the following are equivalent, right? And we can add a couple of things to it. What was our theorem before? We had what one? A inverse exists, right? 2. So this is going to be walk down memory lane here. There exists B such that AB equals to I, right? 3. There exists B such that what? BA equals to I. 4. The column space of A is equal to Rn. 5. The reduced row echelon form of A is equal to the identity matrix. 6. The null space of A is equal to just 0. 7, another way of writing that, AX equals to 0 if and only if X equals to 0. 8, the columns of A linearly independent. 9, what else did I have before? I feel like I'm missing something. Was that it? In terms of our like previous litany of the theory? Oh, we had like AX equals to B, has unique solution for any B, right? If you can solve AX equals to B uniquely for any choice of B, that means that you've got an inverse. So what can we now add to this proud list of equivalent statements? Number 10. Anybody?
Determinant of A inverse 1 over determinant of A.
Well, that's true, but that kind of begs the question. I wouldn't put that in this list. I mean, because this is criteria that mean A inverse exists. I mean, that's kind of a related fun fact. You're in the hunt. If the determinant of A inverse is 1 over the determinant of A, what can the determinant of A not equal to? 0, right, so that's the other one. So yeah, the determinant of A not equal to 0. So, basically a corollary to this, if you've got V1, V2, Vn, a subset of Rn, then let's call this matrix, let's make big V the matrix which is just formed from gluing these guys together. Has the determinant of V not equals to 0 if and only if what? The set V1 Vn is a what? Linearly independent set, yeah. And can you see why this is nice? Like, let's take it out for a spin. Example 2. We've got V1 is 1, 3, 4. V2 is 7, 0, 9. V3 is A, B, C. What does it take? What's the condition on A, B, and C in order that V1, V2, V3 be linearly independent? So what do you gotta do? You just put them together, right? Put them together here. 1, 3, 4, 7, 0, 9, A, B, C. We just need that not equal to 0 for linear independence of the set V1, V2, V3. Now, there are limitations to this, right? The previous things we've talked about, judging linear independence of a set of vectors. We could do it for like, 3 4-dimensional vectors in a 4-dimensional space, right? We could look at a system of equations to decide whether or not those are linearly independent, or we could look at like 5 vectors in a 17-dimensional space, whatever. There's no insistence that we have the same number of vectors as the space we're looking at. But if we are looking at the question of linear independence of a complete, like a set of n vectors in n-dimensional space, in that case, the determinant comes to answer the question nicely. Because I don't know about you, but this is very concrete, right? I don't have to do row operations with like symbolic, with a symbolic column anymore, right? I can just calculate the determinant. How would you guys think I should do it? You know what I'm going to do? To illustrate, I'm going to expand on the middle column. All right, I'm going to do that. I'm going to expand, I'm going to look at the Laplace's expansion by minors with respect to the middle column. And so here's how that goes. So I go plus, I go minus. So I've got minus 7 times the determinant of 3b 4c plus 0 times the determinant. I'm writing it down just for emphasis. 1a 4c, not that that matters. And then minus 9 times the determinant of 1a 3b, I believe. So there's my determinant of v, big V as I'm calling it for the moment, which is what? Minus 7 times 3c minus 4b minus 9 times b minus 3a. And so there you go. You got yourself like a minus 21c. That's a plus 28 minus 9, which is a plus 19b. And then plus 27a. So there you go, 27a. That not equals to 0. There's the necessary condition that these vectors be linearly independent. This also simultaneously answers at least two other interesting questions. What is the condition that these vectors, v1, v2, and v3, thought of as 3-dimensional geometric vectors, be coplanar? What would it take for these 3 vectors, v1, v2, v3, to lie in the same plane? Right? So think about it. If this is instead equal to 0, means v1, v2, v3 coplanar. Because what it would mean if it's equal to 0, it would mean that the set v1, v2, v3 is linearly dependent. Therefore, one of those can be written as linear combination of the other, right? So if you can envision the plane that has, say, v1 and v2, you can build v3 merely from like a linear combination of v1 and v2, subject to that condition, right? Can you guys tell me the other question that this immediately answers without further calculation about the vectors v1, v2, and v3? This goes back to what I said last class. So you need to have you should learn things as soon as I say them, basically, is what I'm demanding of you. Why not? Why haven't you already memorized everything I said? How dare you? Gideon, do better. Sorry. Should I call someone else out? Taryn, why haven't you told me the answer yet? That shrug was like perfect. It was the shrug of complete unintimidation. Thank you for that. It was perfect. So the determinant of 3 vectors concatenated, all right, glued together, also gives us the triple product of those vectors, which remember is plus or minus the volume of the parallelepiped with side vectors v1, v2, v3. So in the context that this is non-zero, it also happens to be the signed volume of the parallelepiped with edges v1, v2, v3. So determinants are pretty cool, right? They do a lot. At the cost of a somewhat quirky formula. Any questions about what I just did? So the rule is, for a 3 by 3, when you're looking at Laplace's expansion by minors, you got to think about this kind of like plus, minus, plus, minus, plus, minus, plus, minus, plus. So what you're looking at is minus 1 to the I plus j for the ij spot. So like 1, 1 is minus 1 squared, and then like 1, 2 is minus 1 cubed, which is minus 1. And so that's why I put a minus, a plus, and a minus. That's where those signs are coming from. If you expand about a different column or row, you have to mind these signs. I usually expand out along the top row because on the top row I just go plus minus, plus minus, plus minus, right? That middle minus for a 3 by 3 is the same minus that you guys always forget when you're calculating the cross product in Calc 3. Not all of you, but some of you. Usually the same ones who forget to check the answer. But oh well, what can we do? Let us go on. So, what I'm about to do, I must look at my notes because what's about to happen here is a little bit tricky. But isn't this a nice update on like the problems we had on the test about linear dependence and linear independence? I think it's a much easier way to think. But again, it does have its limitations. We have to have as many vectors as the space we're looking at. So this brings us to Cramer's rule. All right, so, and here's the deal. This is a proposition, 3.5.1. Be careful to use the same notation as my notes. If AX equals to B is a system, and we're using variable vector x, which is like x1, x2, xn. I'm going to put a transpose on there because, man, this is old. When I wrote this is before I adopted my sneaky parentheses notation. So like, in terms of like my notes and being like forensic analysis on my notes, this is an old proposition. Because I've got the row vector with the transpose. They used to all look like that before I adopted this sneaky parenthetical column vector notation. Anyway. If this is such that the determinant of A is not equal to 0, right? In other words, if you've got a system of n equations and n unknowns, all right? I also have here A is an element of our n by n, but you know, if I talk about the determinant of A, then I'm assuming that A is n by n. All right. Then here's the punchline. X1 is the determinant of A1 over determinant of A. X2 is the determinant of A2 divided by the determinant of A. Xn is the determinant of An divided by the determinant of A. All right, where A sub k is the n by n matrix as follows. So it's basically you've got your like first column A1, A k minus 1, then you put B here, then A k plus 1, An. And here I'm assuming that I can't do that. Rats. Why can't I not do that? I'm a dummy. Why? I can't do that. I've used the A sub, the meaning of A sub n is the matrix, right? So I'm stuck with the clumsy column 1 of A, column k minus 1 of A, column k plus 1 of A, column n of A. So let me just put it in words. A sub k is obtained by taking the matrix A and swapping out the kth column for the inhomogeneous term. I repeat, A sub k is formed by taking the coefficient matrix for the system and swapping out the kth column for the inhomogeneous term of the system. All right? Quick check on the logic. What happens if the inhomogeneous term is 0? Then every single last one of these A sub k's would have a column of zeros. Therefore, those determinants would all be 0. You have 0 over non-zero. all of your x's would be 0, we'd find the unique solution x equals to 0. Hooray, that's what we're supposed to find in the case of ax equal to 0 with a being non-zero determinant. The question then is, why on earth is this true? Right? I mean, that's a crazy formula. Why does this work? So I will show you the proof, which is in lay, which I think it's rather sneaky. And so the proof goes like this. He looks at AE1 equal to column 1 of A. All right? And so forth and so on. Eventually, he gets to AEJ minus 1, which of course gives us column J minus 1 of A. All right? And then next up, he looks at AEJ plus 1 is column J plus. I mean, this is kind of the same thing over and over again, but you get the sense of it here. And then eventually, we get to the nth column, which is the A times En is column n of A. All right, we've talked about this before. When we take the standard matrix and we multiply standard basis multiplied by the matrix, it picks out that column of the matrix, right? And then, so his last equation here is AX equals to B. So we're just making a list, and let me check it maybe twice. Let's see here. So if you look at it, we've got a bunch of vector equations. They've all got the same A on them. So you can just basically, oh, I know what I can do. Oh man, see, if I'd been smarter, I would have written this one in the middle. Never mind, let me just get it. All right, so from this, we get the following. We can write A times E1 E J minus 1, and then you've got E X that X EJ plus 1 En. All right. And that A times this matrix is equal to what? It's equal to column 1 of A, column J minus 1 of A, B, column J plus 1 of A, column N of A. Do you guys agree? So like everything except for the one with the X in it is just the statement that like the matrix times the standard basis gives you the corresponding column. And so like the other identity is like when we multiply A times a matrix, we can do the column by column multiplication. Remember that rule? So this simplifies to like A1, AJ minus 1, AX, AJ plus 1, AN, which is what I have up here, which is equal to column by column what we have over there. All right. Now, let me, for the sake of maybe making this more believable, let me just look at a specific thing here. Let's look at like the 3x3 case when X is in the middle. Let's see what this looks like in the 3x3 case before I just claim something, all right? So like if you look at the determinant, maybe I should write over here. If I have the determinant of like 1, 0, 0, x1, x2, x3, 0, 0, 1. All right, so that's like E1, X, quote unquote, E3, all right? So it'd be kind of like what I'm looking at over there. This would be analogous to this thing right here, but I'm taking the determinant of it. What is the determinant of that? You got x2? Okay. Very good. What would happen if I take the determinant of, well, this one's kind of easier. This is clearly, because it's a lower triangular matrix, that would be just what? x3, yeah? And similarly, you can work out that the determinant of x1, x2, x3 times 0, 1, 0, 0, 0, 1 would be x1. Very good. And, oh, sorry. That was close. I still haven't hit a student this. I still have not hit a student this semester, though, for the record. Although I feel like you may be the first that's been obligated to duck. So it's like you felt like it was necessary. So if we take the determinant of this, what do we got? First of all, this is exactly a sub j. Right? This is a sub j, and I'm going to call this thing Pac-Man. And so what we got is the determinant of A times Pac-Man is equal to the determinant of A sub j, which gives me that the determinant of A times the determinant of Pac-Man is equal to the determinant of A sub j. But what is Pac-Man determinant? If you believe what happened in the 3x3 case, you should believe that generally speaking, what we get there is just x sub j, right? This is actually x sub j. And you can see that if you just kind of expand it out, it's got mostly ones and zeros, mostly zeros and just ones on, you know. So essentially you're looking at like a diagonal matrix. Do you guys want me to write it out? I can try to write it out. So like the Pac-Man, it's 1, 0, 0, 1, zeros all the way down. And then eventually you get to x1, x2, xn. And like in here somewhere there's an x sub j. You'd have 0, 0, There would be a 0 next to the x sub j. There'd be a 1 in the row right above it. All right? And then below it, and then it goes on. So I have a hard time writing this silly matrix out, xn. Then you'd have zeros all the way down to x sub j, and then you'd have a 1 just past it. See, I never make this silly thing big enough. And then it's ones all the way down. So if you like, you could just do what? You could do like column 1 minus x1 column j, right? My bad, my other round. Column j minus x1 column 1, rather. Right? You know, and then column j minus, you know, x2 column 2, and so forth and so on. Basically, my point is, you could do that. You could clear out all of the entries above xj by doing appropriate column operations, none of which cost you any change in the determinant, because the determinant doesn't change under these kind of column operations, because it doesn't change under those kind of row operations, which then would give you a lower triangular matrix with ones down the diagonal and an x sub j in that spot, which then means the determinant Pac-Man is just x sub j. So what we get then is x sub j is equal to the determinant of a sub j divided by the determinant of the coefficient matrix. And that, my friends, is Cramer's rule. We good? Yes, no, maybe so? All right. So now that we have Cramer's rule, we can use it to solve all kinds of things. However, it is actually rather limiting. And the reason that Cramer's rule is rather limited, I should say, is that it only works in one context, which is what? Ah, look at me, erasing the board like some sort of savage. I've got no juice. Oh man. Where's my juice? Got no juice. So sad. All right, so anyway, I'll deal. Happy about this. So Cramer's rule only works if the matrix is invertible, right? So many times we've solved systems and we've had what? We've had the nullity, the number of free parameters in the solution, be more than none, right? And so for any of those problems, Cramer's rule is completely irrelevant. Cramer's rule is only good for systems that have unique solutions. But it is of terrible theoretical importance. So in my notes, I take like a 4-page detour into the theory of differential equations, and I show you how Cramer's rule is used to solve the so-called variation of parameters problem in differential equations. The formulas for variation of parameters arise from solving a given system of equations involving derivatives. And that system, for theoretical reasons, has a unique solution, assuming that you have to start with what's called a fundamental solution set. That fundamental solution set has linear independence, as is judged by something called the Wronskian, and as such, this thing we're doing comes into play, and you can derive the solutions for variation of parameters from Cramer's rule. That's one of its major uses in undergraduate mathematics. I'm not going to test on that in here because, of course, differential equations is not a what? Prerequisite for this class, right? However, we will do some differential equations in here, but the ones I'll actually test you on will actually work out in detail, all right? So that's coming. We're not quite there yet, but we will be using linear algebra to solve differential equations. This material doesn't typically get covered very well in 334 at the moment because our energy is elsewhere, and that's fine. This is the right place to solve those kind of differential equations. So that's what we're going to do in here. In time, not today. So a problem, though, that is interesting is, okay, so if the determinant of A is not equal to 0, then A inverse exists, right? Okay, so find it. What are we trying to solve? Well, we're trying to solve, let's think about this. So we've got A times what? We're trying to solve AX equals to like E, EJ for J equals to 1 to all the way out to N, right? We've got these N systems, right? So, I mean, you could solve these one at a time using Cramer's rule, right? For example, to solve AX equals to E1, how would we solve that? We'd have what? X is equal to what? Well, we'd have X, we'd have X sub, I need a notation for this. Let me call this X sub J. Oof. All right, let me not be an idiot. Let me just show you in the notes because I have forgotten my, oh, wait a second here. I did print them out. It's an easy thing to derive, but if you start in the wrong spot, it's going to go badly. So let me find it. Oh, duh. I can tell you the formula. The formula is this. We'd like to explain why this is the formula. A inverse is 1 over the determinant of A times the adjoint of a transpose. Let me try to unwrap that formula for you. So Cij is equal to minus 1 to the I plus j Mij. What's Mij? Mij is equal to like the matrix of determinant of, let's say, in this current context, A with row I and column J deleted. So let me actually like show you how this works. For example, for a 2 by 2, A, B, C, D. All right. So like M22, rather M, you know, I guess I'm usually put parentheses like that. So Mij here. All right. So what we've got the determinant. What happens if you, so the 1, 1, what happens if you cross out the first row and the first column? What are you left with? Just D, right? And then we take the determinant of C, determinant of cross out the first row and second column, so we got B, and then A. So that's the, and then so the matrix, this is called the matrix of cofactors. I think. I could be wrong. Maybe this M is the matrix of cofactors, and let me, you know, I'm sorry. Let me stop the name calling since I'm not sure which names. I don't want to slander the matrix. You know, let's see here. Anyway, so if that's the case, then what's Cij? So you do what? You got you have to add your plus minus plus sign to those, right? So the determinant of D, of course, is just D. So that gives you D minus C minus B and then A. And then what happens if we transpose that? So I believe this is actually the so-called adjoint of A. So the transpose, listen to me, transpose of that is, yep.
I think the adjoint C and D are in their original places.
Oh, but the transpose.
Oh.
Now they are. And your intuition is right, because you remember that the formula for the 2 by 2 inverse is what? 1 over that mysterious quantity we now know is the determinant. And we do what? We flip the diagonals. And we put minuses on the off diagonal. But that is exactly that matrix right there. So this particular 2 by 2 inverse formula exemplifies the general formula for the inverse, which is given right here by that. And the proof of that is Cramer's rule. It's not hard, but I've got a mental block at the moment, so let me use my projector if you don't mind, if I can find it. Oh, I never told you guys the top hat. My bad. 3178. There you go. I don't mean to deprive you. I know you guys spent, like, you know, lots of money for the top hat. Let's see here, so I don't want to deprive you of your top hat. All right, where was my notes? Here they are. All right. Yeah, the proof is not difficult. You just need to actually like start in the right spot and adopt the right notation and stick to it. So I typically only show you guys proofs in here if I'm expecting you could do it too. And I think this is one of those. Once we like think about it a little bit more and so forth, I think you can understand this proof too, because the proof is really just by Cramer's rule. So all right, so to find the inverse of A, we need to apply Cramer's rule to solve the equations that are implicit within that, right? So I let V1 through Vn be the unknown column vectors of A inverse. I'm trying to solve these equations, right? Bop, 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 bop. But I point out that Cramer's rule actually gives us, so Cramer's rule actually gives us, like V1, the jth component of it actually is the 1j cofactor divided by determinant of A. So that's the thing that you'd, well, uh-oh. I almost feel like I'm going to get electrocuted if I'm not careful in here. It's okay. If I did, it would be hilarious, right? So anyway, this is, I would say this is not altogether obvious, but if you look at what the, what is the, what's the so-called the deleted matrix for Cramer's rule? You know, if we were to look at that carefully, then we could derive these formulas right here, I suppose. But I'm reluctant to actually get into the details here today. Why does it do that? Anyway, so that technical lemma aside, once you can see that, and I don't think it's that hard to see it. That gives us that the jth component of the ith column is Cij divided by the determinant, but the jth component of the ith column is actually the jith component of the inverse. So that gives us, and we end up with the formula that, like, well, anyway, the formula pops out. I'm sorry, I'm not being coherent today for this proof. I tried. But anyway, here's the thing I urged a student once upon a time never to memorize. Here's a 3x3 matrix. And here are the cofactors. Da-da-da-da-da-da-da. All right. And the cofactor matrix is a little bit annoying because it's, well, it's not annoying. It's just what it is. But like 1, 3, I cross out the first and the third column, so I get that DH minus EG. See it? The cofactor matrix here is more interesting, right? So like what is, for example, C22, you get rid of the middle column and the middle row. That leaves you with the edge, the corners, ACGI. So you have AI minus CG. A23, on the other hand, you cross out the second row and the third column, so that leaves you AH minus BG, but it's not AH minus BG because remember there's that plus minus, the plus minus thing is happening. So you got to cross out the row, the column, you got to add the plus minus, and that's how you obtain these. But at the end of it, you have this lovely formula for the inverse of a 3x3. So you're like, wait a minute, you mean I don't need to do row reduction on the super augmented coefficient matrix? I can just write my 3x3 matrix A down, and then I can just remember this formula and just write down the inverse. Yes, this technology could soon be yours if your memory permits you to remember this formula. Now, this formula actually has a lot of beautiful features. Like, it gives you a really snazzy formula for the determinant, which is this. You can kind of see the Fruit Ninja thing I was talking about here. So like, the AEI is like that. And so if I wrote down A, B, C, D, E, F, G, H, I, and then write it again. A, D, G, B, E, H, like that. Then if you look at it, you've got this, that, and that. That's whoop, whoop, whoop. And then you've got GEC, D, I can't ever, these ones minus. That's the Fruit Ninja determinant calculation I was telling you guys about the other day. And these, the pattern here is actually relatively simple to understand. It always involves the components that are not there in that row or column. But there's a complicated plus minus, and then there's also the transpose. There's just a lot. Don't memorize it. Just do the thing we did before. It's just easier. Okay, anyway, I shut up. Sorry guys, didn't mean to go over. Next time I will show you many applications of the determinant. We will see.